Welcome to This Explainer. Today, we're diving straight into the black box of WhatsApp's end-to-end encryption to decode how the whole shebang actually works. I mean, you probably use it every single day, right? You see that little yellow lock icon at the top of your chats, but what is practically happening inside your phone's processor when you hit send? Well, let's find out. Right off the bat, I want you to think about this absolutely crucial question. How can you and a friend agree on a secret code word without anyone, not your internet provider and not even WhatsApp, overhearing it? Because if you just send this secret code over the internet to establish the rules, a hacker could just intercept it, right? It's a classic cryptographic paradox. Okay, so here's our roadmap for today. We're going to cover 1, the lock and key setup, 2, the secret handshake, 3, the double ratchet algorithm, 4, managing multiple linked devices, and 5, what encryption actually cannot protect. Let's just jump right in. Section 1, the lock and key setup. This is the very foundation of the entire system, and it all starts with creating the keys. So WhatsApp relies on end-to-end encryption, which is powered by the open-source Signal protocol. Now, this is a heavily audited cryptographic protocol. And the core idea here, it means the platform provider is essentially acting as a blind mail carrier. WhatsApp only passes scrambled text along. They mathematically cannot decipher your texts. Think of it like a lock and key factory running completely silently inside your phone. Your device automatically generates thousands of public keys. You can kind of think of these as open padlocks. It ships a massive box of these padlocks to WhatsApp servers. Now, anyone in the world can grab one of your padlocks and snap it shut on a message meant for you. But, and here's the absolute magic of it, your phone also generates a single private key. This is the physical master key that unlocks those padlocks, and it never, ever leaves your device. It's not sitting in some cloud, it is strictly on your hardware. Moving on to Section 2, the secret handshake. So how do we actually establish a secure connection using these locks and keys when you want to text someone for the very first time? Using a really clever mechanism called the X3DH, or Extended Triple Diffie-Hellman Protocol, your phones perform a secret handshake. Imagine a giant magic math bowl. Your phone fetches your friend's public padlock from the server and mixes it with your secret private key in that bowl. Meanwhile, your friend's phone grabs your public padlock and mixes it with their private key. Because of the way this one-way mathematical function works, both bowls spit out the exact same secret session key. Both devices calculate it independently on their own hardware. That means the secret code was never actually transmitted over the air to be intercepted. Boom! It brilliantly solves our paradox because there's literally nothing for a hacker to intercept. All right, Section 3, the double ratchet algorithm. Because maintaining continuous security once that initial session key is created is absolutely vital. Having one secret code is great, but relying on just one forever? Yeah, that's incredibly dangerous. You're probably wondering, what happens if someone actually manages to intercept or steal this session key today? Can they just download your entire chat history and read all your past and future messages? Well, in older systems, the answer was yes, but the Signal protocol solves this so elegantly. To prevent mass decryption, WhatsApp uses the double ratchet algorithm. Picture a physical socket wrench that only clicks forward in one direction. Every single time you send a message, the encryption key locks up the text, and then that specific key is permanently destroyed on your device. The ratchet clicks forward to create a brand new key for the next message. This guarantees something called forward secrecy. If an attacker steals your key right now, there is no way they can use it to decrypt old messages, because the keys used for those older messages, they're already smashed to pieces. Behind the scenes, this whole thing relies on a key derivation function, or KDF chain. It is an irreversible mathematical sequence. The moment you hit send, your phone's current key is passed through the KDF, which splits it into two completely distinct outputs. The first is a single-use message key that encrypts your text and then dies in milliseconds. The second is the next sending chain key, which takes the place of the old one. And because your friend's phone is running the exact same math, their keys continuously update in perfect lockstep with yours. But wait, what happens when your friend finally texts you back? A simple one-way chain could still theoretically be vulnerable over a long period of time. So their reply triggers the second part of the double ratchet, the Diffie-Hellman ratchet. Their incoming message includes a brand new temporary public key generated on the fly. This injects completely new mathematical randomness into the sequence. It doesn't just advance the keys, it completely changes their mathematical trajectory. In cryptography, this is known as post-compromise security. It instantly locks out anyone who might have somehow compromised the previous linear chain. Section 4. Managing multiple linked devices. Now that we've covered phone-to-phone, let's pull back the curtain on the actual math and architecture that makes this work when you link your web browser, your iPad, or your desktop app. Just look at this massive 77-digit number. This is the standardized prime hard-coded directly into the WhatsApp application software globally. It's the foundation for the curve 25519 elliptic curve math. Now, I know it feels a little counterintuitive that a piece of the secret calculation is just out in the open for hackers to see, but this proves that the security relies entirely on your hidden private keys, not the public formula. Knowing this massive prime gives an attacker absolutely zero advantage if they don't have the private key sitting safely in your pocket. This modular arithmetic is highly efficient, which is a real game changer because when you link a laptop or tablet, things get pretty complex. Basically, instead of treating you as a single endpoint, the protocol treats every single authorized device as an independent cryptographic identity. So your laptop generates its own completely unique set of identity keys entirely separate from your phone. So when someone messages you, they don't just encrypt the message once. Through a brilliant system called fan-out architecture, your friend's phone checks the server, sees you have a phone, a laptop, and a tablet, and sets up 3 completely distinct mathematical sessions. When they press send, their phone individually encrypts the message 3 separate times using 3 different session keys, bundles them up, and WhatsApp ultimately routes those distinct scrambled packets to each specific device. Of course, if you tried to encrypt a massive 50-megabyte 4K video 3 separate times, it would absolutely crush your mobile bandwidth and battery life. To solve this, WhatsApp decouples the media. The large video is encrypted just once using a random single-use key and uploaded to a server as a scrambled blob. Then, only a tiny text packet containing the download link and the decryption key is sent securely through that multi-device fan-out architecture. It saves massive amounts of data while maintaining that strict zero-knowledge security. Which brings us to Section 5, what encryption cannot protect. Because as incredibly secure and elegant as this math is, we need to bring things back to reality and look at the practical limitations. Encryption is not a magic bullet for all your digital privacy. Look, while your messages are completely secure in transit, end-to-end encryption cannot protect your metadata. WhatsApp still knows exactly who you talk to, when, and for how long. Second is physical device security. If a piece of spyware is logging your screen or, a friend just picks up your unlocked phone, they can just read the decrypted text right off the screen. And crucially, cloud backups. If you back up to Google Drive or iCloud, those chats are fully readable by Apple or Google unless you manually dig into your WhatsApp settings and toggle on end-to-end encrypted backups. So, the big takeaway here is understanding that boundary line. The actual contents of your texts, images, and voice calls are mathematically impenetrable while traveling across the internet. But what is exposed? The fact that you communicated, when it happened, and physical endpoints. The screen you are staring at and your backup settings in the cloud remain entirely your responsibility. And that leaves us with this final thought for our explainer today. The curve 25519 math and the double ratchet algorithms running inside your device are, for all practical purposes, virtually unbreakable by modern computers. But if the 77-digit math protecting your messages is so incredibly robust, is human behavior, our unlocked screens, our cloud settings, our metadata, the final unpatchable vulnerability? Thank you so much for joining me, and I really hope this completely changes how you view that little yellow lock icon in your chats.